Hi. Today I wanted to just go over multiple regression output a little bit. The data I'm going to be using for this I took from example chapter 15, question 5 in the book. It's MLB data, looking at National League teams with winning proportions and home runs and ERA. I've walked through this example in class. I'm going to record a video at some point that walks through this example bit by bit on how to do the problem. But for now, I just wanted to walk through the output to try to make us more comfortable with reading and interpreting multiple regression output. Okay, so the way that we generate these output, if you recall, is we go over to our data tab and we click data analysis, and then once the data analysis window pops up, we select regression and click OK, and then we input our ranges. We have our dependent variable. That range where that data is goes in the top box. The bottom box contains our explanatory variables, which can be 1, just home runs, or ERA, or we can include the full array of explanatory variables. If we do that, we generate the output that I've produced here already. So I'm going to just cancel out of here, and in a later example, I'll show how I got this data. I think I showed you in class. In any case, when we do that, what we get is this right here. We have a table that says summary output at the top. This is a very useful table. I mean, the reason that this exists as a technology is because it does a really good job of summarizing the things that we care about. What do we care about in particular? Well, right now we care about well, the most important thing probably is our estimates of the relationship. Although the f-test matters a lot too. In any case, I'll just walk through what we have here, just so that you can look at this. This has ANOVA right here. That just means that this section analyzes the variance. And it gives us a bunch of different information. We have 3 rows: regression, residual, and total. And then we have 3 sets of degrees of freedom. This is a simple linear regression, so we have 1 degree of freedom in the regression. And this right here, df, is always equal to k. That's k right here. That's how many regressors we have. And you go down here, you can see that we have 1. We have an intercept, and then we have home runs in this case. The dependent variable, I'm sorry, I should have said this. The dependent variable is proportion of games won. So we have 1 regressor. So k equals 1. We have 1 degree of freedom in the regression. Up here we have our number of observations, which gives us n. So we had 16 observations. And if you want to check this, you can go over to the data tab and see that indeed we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 teams. 16 observations, n equals 16. We run a regression. Our total degrees of freedom are that minus 1. So this is n minus 1. Goes here. And then the residual right here is n minus k minus 1. And that's 14. The rest of this box contains more specific information. Remember, the purpose of regression is to give us information about the variability in y. Right? We want to know why all these teams don't have the same winning percentage. Right? Another way to state that question is, why is there variation in y? Why aren't they just all the same? Well, the argument we're making when we do regression is, well, the variation in y exists because there's variation in x. There's also some error, but we're trying to argue that the point that the variation in x is what's driving this result. So what we're trying to measure is we're trying to explain the total variability. And the way we measure the total variability is this number right here. That's the SST, the sum of squares total, the total sum of squares. That's the SST right there. The way we do this is we hope to capture a lot of it with our sum of squares due to regression right here. This is our SSR. This is the amount of the squares that is explained by our regression. The amount that's left over is the sum of squares due to residual, and that's right here. This is our SSE. So that's the information that we have here. Now, if we want to know if our regression does a good job, one way to do that is to take this information and use it to tell us, well, how much of our information did we get, did we capture? To do that, we want to run an F test. We have our F statistic right here, which it calculates for us. This is our F. That's nice. What that is it's, if you remember, it's the MSR, which is right here, over the MSE. So this is getting kind of messy. You can see that this little area contains a lot of information. So we have our F test statistic, and the degrees of freedom come over here. We have 1 degree of freedom in the numerator, 14 degrees of freedom in the denominator. And if you look that up on your F table, you'll see that our significance of our total regression is about 0.13, which is not terribly significant. But that's what our ANOVA table tells us. We can look at other, that's one regression. But our ANOVA table tells us a lot of information about that regression and about the significance of the regression. That's often where I go first. You can see also that this doesn't explain a lot of the variation. Our R squared is up here, right? This is our R squared. And we are explaining about 15% of the variability in Y with our variability in X. Another simple linear regression over here on the ERA tab. So I was on the HR tab, home runs tab. Now we're looking at how winning percentage is related to ERA. ERA is earned run average. It's the amount of runs the team allows. In any case, if you plug in the data, this is what you get. And again, we have a simple linear regression, just one regressor, K equals 1, because we only have one other than the intercept down here. You'll see that the sum of squares total is the same. Right? It's 0.073469. That should be true because it's the same Y, right? We're looking at the same variation in winning percentage, and so we have that information that we're trying to deal with. This regression does a better job. Our sum of squares due to regression is higher, meaning that our variability in X does a better job of explaining the variation in Y. They move together. So again, we have our SSR. All the rest of the stuff is the same. Now we have an F statistic right here that has a significance that's much, much stronger, right? This regression does a very good job of explaining. Or it does a very significant job. They move together. And you can see that R squared right here, that's 0.50. That's high, about half the variation you can explain with just ERA. And then our coefficients down here are useful. So our adjusted R squared, right now we only have one regressor. It doesn't really matter that much. Other stuff that's useful. These coefficients are kind of important. So this is the baseline. So if a team had a 0.00 ERA, it's an out-of-sample prediction, but that would be the predicted winning percentage if the ERA is equal to 0. And then with every additional point of ERA, that winning percentage drops by 0.08. So this, you can use these right here as your intercept and coefficient in the following predicted equation, estimated equation, right? This is what we're really trying to estimate. And B0 is the 0.864. So we could interpret this like so. And then B1 is negative 0.084. And we're going to multiply that by x1, which is, in this case, is our ERA. And that's the estimated equation. I apologize for the handwriting. I'm getting better, but it's going to take some doing. Is this significant? Is this a significant relationship? Well, we have information here. We have our B1. This right here is our SB. That's our standard error on our coefficient. And we have a T statistic, which is just B over SB, right? That's negative 0.08367 divided by 0.02223 gives you negative 3.76. Now this has n minus k minus 1 degrees of freedom, the T distribution. And if we look it up on your T table, you'll see that a p-value, our two-tailed test would give us a p-value of 0.002095. For simple linear regression, this is going to be the same p-value you see as the F, unless you're rounding. If you're not rounding, though, if you're using a computer to do it, those should be the same. But that p-value tells us about the strength of the relationship. All right, now we can look at multiple linear regression. Now we have two. Let me scroll down just a wee bit. There you go. We don't need that top row. But this right here is the full table. We now have two regressors, home run and ERA. And so our degrees of freedom in the regression is 2. We're using 2 of our degrees of freedom to run the regression. And you can see that our R-squared before was 0.5. Now it's 0.858, which is, that's good. We're explaining 86% of the variation. So ERA and home runs, yeah, they do a pretty good job. Not all of it. There are better measures out there in baseball, but that's pretty good. How is this regression significant overall? Well, we look at our F-test and you see that significance, 3.05 e to the negative 0.06. That's equal to, the way we do that is we write 3.05, and then we move the decimal point back 6 spaces because that negative 6 is there. So 1, 2, 3, 4, 5, 6. That's the decimal point. We have 0, 0, fill in zeros here. All right. That's pretty improbable. 0.000000305. That's our p-value. That's what that's saying. That's our p-value on the F-test. So yes, this is very highly significant. Other than that, well, now we see we have positive relationship between home runs and winning percentage, negative relationship between ERA and wins, and the p-values here are all. Where's my pen? There we go. These p-values, they're all really small, right? Everything's significant. So yeah, so that's how you read a regression table. We'll do more practice. Everybody will get good at this. We'll take our time. But yeah, it's good to take a look at this, and I'll save this spreadsheet so you guys can take a look. Thanks. Bye.